Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So today we are doing another awesome video, and today is on nuclear chemistry. Okay. But before we start this video, I want to make sure that you understand a few things, and that is you're going to make sure that you understand the atomic structure and nuclear chemistry. Video series. And so look up on my YouTube channel and please watch the atomic structure collection as well as the nuclear chemistry collection before you start this. There are many example problems within there that are really critical. All right, so a few things that we need to know before we start this nuclear chemistry worksheet. So let's get moving here. All right, so before we get this going, let's cover a few items that are actually critical to this understanding. All right, so let's zoom in on this here information, and then I'm going to help you out here. So real quick introduction to nuclear chemistry. You need to understand a few different types of particles, okay? And that would be the following. An alpha particle. What is an alpha particle, first of all? Okay. An alpha particle is a helium nucleus. And this is the symbol of it in its standard nuclear notation. So when something undergoes alpha particle emission, you're going to start off with the AXZ standard nuclear notation of the element of interest. It's going to disintegrate or decompose, and you're going to end up with an alpha particle. The atomic mass is going to decrease by 4. The atomic number is going to decrease by 2. And then you're going to have to look up on your periodic table the new element that's formed. All right. Second is beta emission. Beta emission is symbolized as this right here. What is a beta particle? Is it effectively an electron? Okay, and that's why there's the beta symbol right there, a 0 mass and a -1 charge. That's letting you know it's an electron. It's in the AXZ format for your starting element, and it's going to also decompose into a beta particle, and the atomic mass will not change from that of the original. However, the atomic number will be increased by 1. You're going to have to look up the new atomic number to acquire the new element symbol. Then third is gamma emission. Gamma emission is the gamma symbol here. And you should see with this one here that the mass for the gamma particle is 0. The charge for the gamma particle is 0 as well. And so what happens is that you start off with your standard nuclear notation of your element or isotope of choice. It undergoes gamma emission, and you end up with the same element, the same mass, the same atomic number, that is the same element. What has actually changed between the reactant and product of that same element? Well, it is actually that the product has decreased in energy. The nucleus has become more stable because it has emitted and released some energy. That's one of the important components. However, the atomic number and nor the atomic mass have changed in the process. Okay, some other things that you need to know is the following. So let's see if I can zoom on out here and get all of this on here. And let's focus this here again. Perfect. Okay. Alpha particles can be either written of one of 2 ways, and it's 4242. That part is constant, right? It is either the alpha symbol or the helium symbol, because this is really a helium nucleus. It has a mass of 4 and a charge of +2, okay? Beta particles can be written one of 2 ways, and that's a beta symbol or an E. And the mass is 0, the charge is -1. That's because the beta particle is effectively an electron. Okay. Alpha particles are essentially a helium nucleus. They have a +2 charge, and they can be stopped by the first layer of skin or a sheet of paper. They have relatively slow velocities because of their relative high mass. Beta particles are essentially electrons, and they have a -1 charge. They can be stopped by wood, plexiglass, 1 centimeter of aluminum, any low-density objects, and are relatively high in velocity since their masses are relatively low. Gamma particles, however, they are a photon, i.e. that is light. They do not have a charge, they do not have a mass, and they are stopped by 13 centimeters of lead or other high-density objects. And they do travel at the speed of light. All right, cool. Now, that is kind of the first half of our nuclear chemistry worksheet. We have some half-life calculations that we need to do. So I'm going to roll into the second half of this. Okay. All right. So this is the second half right here. So some really important equations that you might want to know are the following. In order to determine half-life calculation problems, you're going to know either 1/2 to the power of the number of half-lives times the original amount equals the amount remaining. This is a very, very useful equation here. Okay, so this is a constant, this 1/2, and then the number of half-lives. It's not the half-life time. It is the number of half-lives times, would be times the original amount that you had, and then that equals the amount that remains after a certain number of half-lives. Really important equation. All right, now, depending on what math level you are in, you might find that another equation can be useful as well, and that equation is the integrated first-order rate law. And this process works with non-whole half-lives, and it will work for other problems that are actually more difficult. This is the natural log x sub t, that's concentration at time t, divided by the concentration at time naught, that's concentration at time 0, is equal to negative kt. Okay. So x sub t is the amount at time t, x sub naught is the original amount, k is the rate constant that will be per unit time, t is the total amount of time. Now this integrated first order rate law right here goes hand in hand with the half-life equation here. You need two of these equations, either substitute them in or work with them in sequence to be able to solve them most commonly. Is the half-life equation, it works in conjunction with the integrated first order rate law. T of 1/2 is the half-life equals natural log of 2 divided by k. What holds these two equations together is k, which is the rate constant. That is the thing that holds these two equations together with a similarity between the two. There is one other method besides using these two equations, and that other method is, I call it the beat it with a stick method, chop it with an axe, hack it with a knife, or doing a table method. And that is, you're going to take whatever you have, and then what you do is you actually slice it in half. So you actually take a knife and you just slice it in half. You take that sample, slice it in half, slice it in half, slice it in half, slice it in half, and then you should get what you are looking for then. So anyways, I don't know if that works for you. What equation you like is up to you entirely, right? So you could use this special half-life equation, which is 1/2 to the power of number of half-lives times the original amount equals amount remaining, or alternatively, you can use this integrated first order rate law with the other half-life equation. So either one. So that gives you a little bit of a summary on what you need to do here. So now let's get into some equations and some problems so that we can actually do the math. Let's do it, folks. And I'm so excited. Just a real quick little reminder, I am the Crazy Hat Chemist, and you are watching the most valuable videos here if you actually want to learn chemistry and be productive in chemistry. So I will give you a strong foundation in chemistry so that you can move on to any college, university that you would like to. That's what this class is all about. All right, so here we go without further ado. All right, so what we're going to do is we're going to peel this away and we are going to put on our worksheet and zoom into certain sections here. So here is our nuclear chemistry worksheet. And let's see if we can solve these problems here. So put on my little paperweights here. I like to use those. The other thing that you need during this whole entire worksheet is you do need most certainly a periodic table. And specifically, I am using this periodic table. You have seen it before, and you're going to see it again, most certainly guaranteed. All right, so let's start these first set of problems. Okay, so this first one, it says uranium-238 undergoes alpha decay. So what we first need to do is write out the symbolic standard nuclear notation for the uranium isotope here that's given, and that's AXZ. So we're going to be using AXZ constantly here initially. So uranium, that's a U from our periodic table. So we can verify that here really quickly here. There's uranium, and that is atomic number 92. That's going to be critical here. So we've got uranium 238 and 92 is the atomic number. Okay, so what I'm going to do is I'm going to zoom in on here and do these problems a little bit bigger and bolder so that you can see them a little bit more clearly. There we go. I think that's just a little bit better. Yeah. All right. Perfecto. All right, so uranium undergoes alpha decay. Now remember that all of these are decay processes, and if they are decay processes, then you start off with one reactant. That's what we've done there, and we go to products. And so what you need to know is the alpha symbol and its numeric values. That is 4, 2, and the alpha symbol there like that. So these are really quick arithmetic problems here. This is not like rocket science or anything like that. Okay, and so what we want to do is we want to get the A, the X, and the Z for our product. And in order to do that, what we need to do is we need to do the quick little simple math that's associated with this. So you can do this off on your own, and it is really, we're going to take numerator here. And the numerator is as follows. 238 is equal to 4 plus A. And what we're doing is we are solving for A. So we're going to subtract 4 on both sides, and we get 234. So our A is 234. I'm going to erase that A that was there in the background. I'm going to now solve for the Z, and the Z is 92 is equal to 2 plus Z, right? So we're solving for Z, and we're going to subtract 2 on both sides, and what number do we get? We get the number 90, just like that. Okay, and now what we need to do is look on the periodic table and find the element 90. And so we're going to look on a periodic table. We're going to find the element number 90 right there, and that's thorium. That's TH. So now we have TH. And that is our symbolic notation that we need to write. This is the entire equation. And what you need to do before you actually are done is you need to make sure that this is correct. So really simple to check if it's correct. 234 plus 4, does that equal 238? Yes, it does. 90 plus 2, does that equal 92? Yes, it does. You can effectively view this arrow as a giant equal sign. Okay, and then you're going to double check that number 90 is actually thorium that's on our periodic table. And that is also correct. So make sure that all that works perfect for you. Let's get on to the next problem, problem number 2. All right, so let's get moving on to number 2, like I said before. So here we go. We're going to write thorium-234 undergoes beta decay. So we're going to start off with thorium and 234. And what is thorium? This is thorium right here. So it's atomic number 90. So we have TH. That's atomic number 90. Its mass is 234. Undergoes beta decay. So beta particle 0, -1 plus, and what we are looking to solve for is AXZ, right? So everybody's got that format. So I'm going to erase this because that's what we're going to be solving for. Okay, and so we've got 234 is equal to 0 plus A. And so we're solving for A. A is 234. 234. Fantastic. 0 is equal to -1 plus Z. And so we're going to add 1 to both sides. That will be 91. And we got 91 right there. And that's, we're going to look on our periodic table for element number 91. And that's right here, element number 91. And that's PA. Really simple there. So that's PA. Fantastic. Done with that one. Pencil drop. Next one is uranium-234 undergoes alpha decay. So we already found uranium on our periodic table. That is right here, element number 92. Okay, and we're going to undergo alpha decay. So it's uranium-234, that's element number 90, undergoes alpha decay. That's 4 and 2. And that is an alpha symbol there like that. We're solving for AXZ. So it's 234 is equal to 4 plus A minus 4 on both sides. And we get 230. 230. And then it's 90 is equal to 2 plus Z. And so we're going to subtract 2 on both sides. And we're going to get the next number there. And, oh, wait. I made a mistake here. Uranium is 92. I apologize. I was thinking too far ahead there. Okay, so 92 is equal to 2 plus Z. And so we're going to subtract 2 on both sides, and we're going to get 90. We're going to look on our periodic table. We're going to find element number 90. And let's see if we can do that here. Let's hold this over just a little bit. What is element number 90? It's right there, and that's TH. We've done that already today here, just on problem number 1. So there we go. And notice that problem 1 and 3 are very similar, except that they are completely different isotopes of the same element. That's what that is. The next one is radon-222. And so radon is Rn, and that's 222. And just to double check here, we're going to find on our periodic table radon. There's radon. That is atomic number, element number 86. So we're going to write that down here. So 86 undergoes alpha decay. That's a 4, a 2, and the alpha symbol plus AXZ. We're going to solve for the A. That's 222 is equal to 4 plus A. Subtract 4 on both sides, and you should get 218. 86 is equal to 2 plus Z, and we're going to subtract 2 on both sides, and we're going to get 84. We're going to look up 84 on our periodic table, and that is right here, 84, and that's polonium. That's PO, just like that. All right, fantastic. Next one is polonium-218 undergoes alpha decay. So that's 218. And we just found polonium. That is 84, and that's PO. It undergoes what's called alpha decay. So that's 4 and 2, and there's an alpha symbol. So we're solving for the AXZ. So it's 218 is equal to 4 plus A. Subtracting 4 on both sides, you should get 214. And then it's 84 is equal to 2 plus Z. We're going to subtract 2 on both sides. We're going to get 82. And we're going to look on our periodic table, and we're going to find element number 82. 82 is right there. That's, whoops, sorry. 82 is right there, and that's PB for lead. So PB, just like that. All right. Next one is lead-214. So we just found lead. That's PB. That's 214, and that's element number 82. That undergoes beta decay. So that's 0, -1. That's the beta symbol plus AXZ. We're going to solve for the A. So 214 is equal to 0 plus A. Subtract 0 on both sides. I get 214. The mass does not change with the beta particle. And then 82 is equal to -1 plus Z. And so we're going to add 1 to both sides, and that will give us 83. 83. Now I'm going to look up number 83 on my periodic table, and 83 is right here. Man, this is none of your bismuth. Yeah, that's a little chemistry joke there for you. So that's bismuth. All right, fantastic. We got that one nailed. Now, what we're going to do is we're going to slide this over to the next set of 5 problems that are very similar to these previous 6 right here. All right, so we're going to be doing the same pattern that we just did. So let's slide this on over here. Here we go, and let's see if we can nail down these problems right here. Cool. All right, so this next one here is bismuth 214. So we just did that. That is bismuth, and it is 214. Bismuth is atomic number 83. It undergoes gamma decay. So that's gamma particle 0 and 0 plus. And so what we have now is a real simple AXZ pattern here. We're going to solve for A. That's 214 is equal to 0 plus A. Subtract 0 on both sides. That's 214. The atomic mass does not change with gamma radiation. And then 83 is equal to 0 plus Z. Let's subtract 0 on both sides. We get 83. And this one is really easy because we already had looked up 83. That's bismuth. This is bismuth. Just note that this product here, not that you do need to note it, you do not need to note it, but this product is lower in energy than the reactant is. That's what happens here. Next one is polonium 214. So 214, and then polonium is PO. We had looked this up earlier here, and so let's just verify that polonium is right here. So polonium is right here, and that is element number 84. Okay, so this is 84, like that. Undergoes alpha decay, that's a 4 and 2, and there's the alpha symbol. We're looking for the AXZ. That's 214 is equal to 4 plus A. We're going to subtract 4 on both sides. We're going to get 210. And then 84 is equal to 2 plus Z. We're going to subtract 2 on both sides. We get 82. And so now this one, we need to find element number 82. And we've done this one already before as well. 82 is PB. That's for lead. So this is PB, just like that. All right. Let's do the next one. It says lead 210. So we've got our 210. We've got our PB. We looked up 82 just previous to this. Undergoes beta decay. That's 0 and -1. And there's our beta symbol. So 210 is equal to 0 plus A. This will be 210. The atomic mass does not change with beta decay. And then 82 is equal to -1 plus Z. So we're going to add 1 to both sides. So we're going to get 83. So we're increasing the atomic number. Okay. And so we're going to look up 83 on our periodic table. And we have also done this one before. That's bismuth. Like it's none of your bismuth. Okay. All right. Perfect. The next one is bismuth 210. So we have the 210, we have the Bi. We just did bismuth. This is an 83 like that. It undergoes beta decay. That's a 0, -1 beta decay plus AXZ, right? I'm hoping you're remembering what I'm talking about when I talk AXZ. AXZ, and I'm solving for the A, then the Z actually in order to get the X. So, all right, just to make sure that we're on the same page. So 210 is equal to 0 plus what number? That would be 210, of course. And then 83 is equal to -1 plus Z. Add 1 to both sides. That's 84. We're going to look up number 84 on our periodic table. And we've done this one already before too. 84, and that's polonium. So we're going to write that down, PO. And we have one more of these to do. We have polonium 210. So that's PO 210. And that's 84. It undergoes alpha decay. That's 4 and 2. There's the alpha symbol. AXZ, let's solve for that A. 210 is equal to 4 plus A. We're going to subtract 4 on both sides. We're going to get 206. 84 is equal to 2 plus Z. Subtract 2 on both sides, we're going to get 82. And then we're going to look up element number 82. 82 is PB, that is lead, so that is right there like that. All right. So that nailed down our first set of few problems right there. So that hopefully wasn't all that bad. So let's do our next set of problems here. So we're going to slide this down and zoom on out simultaneously so that we can see these problems here. All right, so I'll just move this over here so that you can get a zoomed out version of all of the problems 1 through 11, and so that you can see that right now. So hopefully you can see all the problems 1 through 11 and their answers. Perfect. Looking good, I think, so far. Just a quick little shameless advertisement. I am the Crazy Hat Chemist, and this is the nuclear chemistry worksheet number 1. I don't have 2 of them. This is the only one I have. So nuclear chemistry worksheet number 1. And we are doing these nuclear chemistry worksheet problems here. Before you actually do all these problems, you should watch my videos so that you understand what's going on with the lecture portion of this. All right, so without further ado, please like and subscribe, and let's get on with problem number 12. So let's hit number 12 here. It says uranium-238 undergoes a series of alpha, alpha, beta, gamma, alpha, beta, gamma decay. Write the equation and identify the product. So this really isn't too bad. What we have done with all the previous problems, 1 through 11, we've done them individually. Now what we're going to do them is just one fell sweep of a problem. So uranium, that's atomic number 92, that's 238, undergoes alpha. So that's 4 and 2, that's alpha, plus another alpha, 4 and 2, that's alpha, then a beta, plus 0, -1, that's a beta, plus a gamma, that's 0, 0, and the gamma, plus the 4 and 2 for the alpha, plus the 0, -1 for the beta, plus the 0 and 0 for the gamma. Plus, now I'm looking for A, X, Z. So of course I need to solve for the A individually, the Z, and then I'm going to look up on my periodic table what the Z is to get the X. Okay, so really simple problem here. We just need to sum everything all together. So it's hopefully not so bad that way. So what we're going to do is we're going to sum up our numerator terms here. Okay, and so that's 4 plus 4 plus 0, that's 8 so far, plus 0, that's 8, plus 4 so far, that's 12, plus 0, that's still 12, plus 0, that's still 12. So we're going to say 238 minus 12, and I get 226. So my A is 226. Okay, perfect. Then what we're going to do is do 92 minus whatever 92 is equal to 2 plus 2, that is 4, right? Minus 1, that is going to be 3, plus 0, that's going to be 3, plus 2, that's going to be 5, minus 1, that's going to be 4, plus 0, that's still going to be 4. So we're going to say 92 minus 4, that's going to be 88. Now what we're going to do is we're going to look on our periodic table, find atomic number 88. And so we need to do that here. Just going to fold this over again, and 88 is right here, and Ra, radium. Perfect. So Ra. So there's our entire mathematical equation for that one. It's really not too bad. You just got to do them in sequence and stay with those numbers. All right, let's do our next problem here. It says platinum 198. So 198, that's PT for platinum. We're going to find platinum on our periodic table, and it is atomic number 78. That is PT. It's right next to gold. Okay, so PT was atomic number 78. So we're going to write 78 right there. It says it undergoes a series of decays of alpha. That's 4 and 2. That's alpha. Plus a beta. That's 0, -1, beta. Plus a gamma, 0, 0, gamma. Plus an alpha. That's 4 and 2 for the alpha. Plus a 0, -1 for the beta plus, and now I'm solving for the AXZ. So I'm doing something similar that I did last problem on problem 12 for problem 13. So we've got 198 is equal to 4 plus 0. So let's do 4 plus 0 is 4, plus 0 is still 4, plus 4 is 8, plus 0 is still 8. So we have 198 minus 8. That's going to equal 190. So 190 right there. Then we have 78 is equal to 2 plus -1. So that is, so 2 plus -1, that's 1 plus 0, that's 1 plus 2. That's going to be 3 plus -1, that's going to be 2. So it's going to be 78 is equal to 2 plus z. So we're going to 78 minus 2, and we're going to get 76. And then we're going to look up atomic number 76 on our periodic table. And that is right here, 76, and that is osmium. O-S. If it was O-Z, it would be for Ozzy Osbourne, but it's not. Okay. All right. Fantastic. So I think we've got that nailed. So let's do some of our other problems here. And we're going to stick with this set here, right here. So number 14, it says when a hydrogen 2 atom and a hydrogen 3 atom combine to form a helium 4 and a neutron and energy. This is an example of nuclear what? This is nuclear fusion. Okay, that's a combination. The nuclear reactions that take place in the nuclear reactor of power plants are fission or fusion. So fission is splitting, fusion is combining. And well, that would be fission reactions. Everything on our planet is fission reactions. All right, next one. Nuclear fusion is what takes place in the sun. True or false? That is true. Next one, number 17, it says atomic bombs are uncontrolled chain reactions of nuclear fission. So is that true or false? That is also true. Okay. All right. Fantastic. I think we have nailed down problems 1 through 17 on this worksheet so far. And let me just zoom out a little bit so you can see all of these problems on this problems 1 through 17 on this worksheet here. Let's see, here we go. This is going to work out better. Guaranteed. Okay, so that's what we have done thus far. I think that's looking pretty good. Okay. Just remember, I am the Crazy Hat Chemist, and I am here for all your crazy hat chemistry needs. If you want to learn chemistry, then this is the place to come if you actually want to learn chemistry such that you become a chemist, or if you need chemistry for any future of your life in some way, shape, or form, this is the place to come for your chemistry needs. You want to do well in college in chemistry? This is the place to come. Anyways, we got another second half of this worksheet. We have problems 18 through 25, and that's going to be in the next video here. So I'm going to hit the stop button on this one. You're going to like and subscribe to my YouTube channel. I would greatly appreciate that. And I'm going to see you next time for the second half of this video. All right. Cheerio. Bye for now.